As large language models grow in size and complexity, serving them efficiently has become one of the hardest challenges in AI. A single GPU instance is no longer enough because models span multiple nodes, GPUs, and demand careful consideration at every layer. And as we push further with reasoning models and agentic workflows, the stake only gets higher. Hello everyone, I'm Sanskriti Harmukh, a developer relations at Vultr, and in today's Tech Talk, we will take a deep dive into how NVIDIA Dynamo is built to tackle exactly these challenges. We'll cover disaggregated serving, see how Dynamo routes requests with KV cache awareness, the open source inference engine it supports, how it plans and scales GPU resources dynamically, and how you can observe the entire pipeline in production. So, without any further ado, let's jump right into it. NVIDIA Dynamo is an open source modular inference framework designed from the ground up for distributed environments, meaning it doesn't just run on one machine, rather, it orchestrates inference across entire GPU fleets. Dynamo disaggregates inference phases across different GPUs, separating the work of processing a prompt from the work of generating tokens and assigning each to the hardware best suited for it. Beyond disaggregation, Dynamo avoids one of the most costly problems in distributed inference, that is, redundant computation. Through intelligent request routing, it ensures that requests are always routed to the GPU that already holds the relevant context, eliminating unnecessary recomputation. And finally, because GPU memory is expensive and finite, Dynamo extends it by tiering KV cache across CPU memory, SSD, and object storage, keeping the most critical data on GPU while offloading the rest to cost effective storage without sacrificing user experience. Now, let's go one level deeper to understand disaggregated serving. In traditional LLM inference, both prefill and decode phases run on the same GPU. Prefill processes the entire input prompt in parallel and is memory bound, whereas decode generates tokens sequentially and is compute bound. But running both on the same hardware means neither phase is fully optimized, and at a scale, this becomes a serious efficiency problem. Disaggregated serving solves this by separating the two phases across different workers. Prefill workers focus solely on processing the input prompt and generating the KV cache, whereas decode workers focus solely on token generation at high concurrency. Each can now be independently scaled and optimized for its specific computational characteristics. But deciding whether to use disaggregated or aggregated serving isn't always obvious. This is why Dynamo includes AI configurator. It takes your model, GPU count, and SLA targets, evaluates both architectures, and automatically determines the optimal configuration. Now that we understand how disaggregated serving is split prefill and decode across dedicated workers, it raises another critical question. Once KV cache is generated across multiple workers on a large GPU fleet, how is it managed efficiently? Well, this is exactly what KV Smart Router and KV Cache Manager address. In a disaggregated setup, every prefill worker generates KV cache for the prompts it processes. When a new request arrives that shares context with a previously processed prompt, and if that request is routed to a different worker, then the KV cache has to be recomputed from scratch. At scale, across large GPU fleets handling thousands of concurrent requests, this recomputation becomes extremely expensive in both time and compute. The smart router solves this directly by maintaining a global awareness of which KV cache blocks exist on which worker across the entire fleet. So, when a new request arrives, instead of blindly load balancing, it routes that request to the worker that has the highest KV cache overlap, maximizing cache reuse and minimizing costly recomputation. But even with perfect routing, KV cache is large. As sequence length grow and concurrent request piles up, GPU memory fills up fast. This is where KV Cache Manager steps in. It is a cost-aware offloading engine that transfers KV cache across memory hierarchies from GPU to CPU memory, SSD, and even to object storage. freeing up valuable GPU memory while ensuring the cache is accessible when needed. Now that we understand how Dynamo manages KV caching and routes requests intelligently, let's look into what inference engines runs underneath all of this. NVIDIA Dynamo is designed to be engine agnostic, bringing disaggregated serving to open source inference engines without locking you into a single backend. It currently supports three. VLLM is the recommended choice for most production serving use cases. Its page retention mechanism manages KV cache in non contiguous memory, enabling high concurrency without memory fragmentation, making it well suited for large GPU fleets handling diverse workloads. SGLang, on the other hand, is optimized for cache heavy and agentic workloads through Redux attention, which efficiently reuses KV cache across shared prompt prefixes. Lastly, TensorRT LLM is NVIDIA's own optimized inference engine built with fused kernels and hardware specific optimizations that extract maximum throughput from NVIDIA GPUs, making it the right choice when raw performance and hardware efficiency are the primary objective. With the inference stack now fully in place, the remaining challenge is knowing how many workers to run at any given time. Inference workloads are inherently variable. Request rates fluctuate, sequence lengths are unpredictable, and over provisioning wastes expensive GPU resources, while under provisioning violates your latency SLAs. Dynamo's GPU Resource Planner solves this by proactively monitoring the prefill queue depth and decode KV cache utilization, giving it a real time view of pressure building across both phases before it impacts user experience. To stay ahead of demand, the planner uses predictive load modeling, choosing from a REMA for time series workloads with trends and seasonality, Common Filter for fast online forecasting with a smooth adaptation, or Profit for complex seasonal patterns. These models forecast the next interval's request rate, input and output sequence length, and calculate exactly how many prefill and decode replicas are needed. The planner then scales workers dynamically to meet your declared SLA targets while staying within your defined GPU budget. With all the information that we have captured so far, we cannot forget that a production inference system is only as reliable as our ability to see inside it. NVIDIA Dynamo addresses this by exposing inference metrics across all components designed to integrate with the standard observability tooling. The Dynamo frontend exposes a metrics endpoint that Prometheus scrapes continuously, collecting TTFT, ITL, ISL, and OSL metrics across every request flowing through the system. The GPU Resource Planner then queries Prometheus at every adjusted interval, using the metrics collected to calculate predict load and determine the optimal number of prefill and decode worker replicas needed to stay within your declared SLA targets. All of this is also visualized through the Grafana dashboard, giving operators full visibility into how the planner is behaving and whether the system is meeting its SLA targets at any given moment. And that brings us to the end of our deep dive into NVIDIA Dynamo. From the core architecture of disaggregated serving through intelligent KV cache routing, backend engine support, GPU resource planning, and full stack observability. If you would like to go beyond the theory and get hands on, we have published a complete set of NVIDIA Dynamo guides on the Vultr docs covering everything we discussed today. Also, if you would like to experience this on NVIDIA GPUs, then use the promo link attached in the description below to claim $250 in free credits on a new Vultr account. Now, to continue the conversation, ask question or share what you built, join the Vultr community forum. Thank you so much for tuning in. We hope this tech talk gave you a clear understanding of how NVIDIA Dynamo is reshaping distributed LLM inference at scale.